we are going to look at the cleavage of an ether with a hydrogen halide. This will result in the formation of an alcohol and an alkyl halide as the result of this. Now you can do this with symmetrical or asymmetrical ethers. To be a little different from what's in your book, I'm going to use an asymmetrical ether. But this is typically done with a symmetrical ether, something like diethyl ether. But I am going to show something different. And I want to do this in such a way that the two carbons that are attached to this particular oxygen are not chemically equivalent, because the one on the left is a primary carbon and the one on the right is a secondary carbon. And there will be some selectivity issues as we go through this. So on the arrow, what you would see is a hydrogen halide. This could be HI, HBr, or HCl. Those are the ones that are typically used. And you heat this up. Now the acid that you use needs to be concentrated. In other words, you would not want it dissolved in water, since this is a reaction that is an equilibrium reaction. If you start out with the alcohols, it would tend to favor the formation of the ether. If, on the other hand, you don't have water or any alcohols present, it tends to favor the formation of the alcohols. So ethers here would be the solids, and as you know, they are liquids most of the time, and they're very volatile. So what happens here is you still have a strong acid. And I hope you remember, strong acids like the hydrogen halides are very good proton donors. So we are going to be donating a proton to this ether. Now the only atom of the ether that can act as an electron pair donor is the oxygen, so it will donate one of its lone pairs to pick up the proton. This shouldn't be anything new to anyone. Once this has occurred, you will make one of these alkyl oxonium ions that we've seen so many times in organic chemistry. You'll have the corresponding halide as well. Now what you've done is basically created a very good leaving group. This is very similar to a hydronium ion or any other alkyl oxonium ion. Excuse me. Basically what you have a choice here of is two different carbons to do an SN2 substitution at. And this can actually occur either of these two carbons. But hopefully you remember with SN2 substitutions, you're more likely to react with the primary carbon than you are a secondary. This would not do SN2 chemistry with the tertiary substrate. So we do typically use primary carbons. Secondary are possibilities, tertiaries are very rare. But the primary carbon here, the one on the left, is much more likely to undergo this nucleophilic substitution. So I'm going to show the major route here in red, but you come in here and do this backside attack and kick out your leaving group. That's an SN2 substitution. Because this is an asymmetrical ether, you could also do it on the other side. If it were symmetrical, you could do it on the other side as well. You just end up with the same products. So in green, I'm going to show what happens for the minor product. It would do this backside attack, and again, you'd kick out your leaving group. So if we're following the red route, you'll have had the halogen add to the primary carbon. And you would have kicked out the corresponding alcohol. If, on the other hand, you wanted to go the other way, which is a possibility, you will produce the minor products. And again, if this had been a symmetrical ether, you would have had the same products coming and going. It wouldn't have mattered which way you had gone and done this. Now, be aware that you are still in strong acid, and so these alcohols that are produced are likely to undergo protonation again with the HBr. So I'm going to show that with your major product. But in the end, these are the two products you care about. It's just that you're still in strong acid. So what happens here is, again, you would be giving up the proton. Your oxygen would pick up the proton. And this happens with the minor product as well. Again, I'm just not showing that one. You get here. And at this point, the halogen will then do the backside attack again. You will kick out your leaving group, and in the end, you have yet another alkyl halide, in this case water. So this is where you could go for your major, and you would also have from previous this guy. And if you'd gone the other route, you'd still get these as your major and minor products, since they would undergo the same reaction. So if you have two equivalents of that hydrogen halide, and since you are doing this in concentrated solution, you will end up with the two alkyl halides. So this goes all the way to the two alkyl halides if you do this in a concentrated solution.